So question 11.1 says in the diagram chords DE, EF and DF are drawn in the circle with center O. KFC is a tangent to the circle at F, and we need to prove the theorem which states that DFK is equals to E. So DFK is this angle. We need to prove that it's equals to that angle. So what we want to do is we want to construct a diameter BF. So another point B somewhere here. So construct a diameter line that goes through the center and goes to B. Something like that. Then, so construct, that's step number 1, construct diameter BF and draw BE. So we then connect these points together like that. Then what we want to do is we want to prove that BEF will be 90 degrees. So BEF, this angle here is 90 degrees. And we also want to prove, or we also know that this will be 90 degrees. Then we can use certain laws to prove that some of the angles will be complementary. So 90 minus BFD. So BFD in this case will be BFD, this tiny little angle here and that tiny little angle. But let's continue with the proof so you can see this. So after constructing the diameter and drawing the line BE, our first step is to say BFK is equals to 90 degrees. So this here is 90 degrees. BFK equals 90 degrees. Or you can say DFK is equals to 90 minus BFD. So next step would be DFK is equals to 90 minus BFD. So BFD. So the reason for this top one is simple. That's just the radius x tangent. So whenever a radius, a line from the center meets with a tangent, they form a 90-degree angle. Then here, this is just simple manipulation. We can say that DFK, which is this smaller one, is just 90 minus this other smaller one over there. So that's what we currently have so far. We expressed this angle in terms of this smaller one over here. Then from here, we will say that BEF, so BEF is also equal to 90 degrees, and this is angles in a semicircle, angle in a semicircle. And from here, we can then say that DEF, so DEF is this small section here, which is what we are partially interested in, also known as the angle E. DEF or E is equal to 90 minus BED. As you can see, we're just stating what we see. If this is 90 degrees, then this angle here will be 90 minus the smaller portion, BED. Then we know that BED will be equal to BFD. So BED is equals to BFD, which is angles in same segment. Like that. So we can then take this and say that DEF is equals to 90 minus BFD, since BFD and BED are equal. Then, since we have now expressed DEF in terms of BFD, and we've also expressed DFK in terms of 90 minus BFD, and we see that they are the same, we can therefore say DFK is equal to DEF. And remember, DEF in this case is just the angle E, so you can write E, and then that is proved. Or we could use another method, and in this method what we do is we construct two radii. So we're gonna have a radii that goes to DO, and a radii that goes, or radius that goes from D to O, and another radius that goes from O to F, like that. So that will be step number 1, construct radii DO and OF. Then next we're gonna say that OFK, just like before, OFK is equals to 90 degrees, and this is radius perpendicular with tangent. Then from this we can say that we can say that DFK is equals to 90 minus OFD. So DFK, smaller one, is equals to 90 minus this other smaller one, and that's what we have in this regard. Let me make these dotted lines for our radius like that to show these are constructions and not actually part of our drawing. Then after this we can say that ODF is equal to OFD. So ODF is equals to OFD. This is because properties of isosceles triangle, like that. Because these two are radius or radii, it allows us to equate these two smaller angles there. Cool. So after we do this, we can now formulate an angle for DOF and say that DOF is equals to 180 minus 2 times OFD. This is just interior angles of a triangle. So interior angles of triangle, like that. And then we want to write now DEF as equal to 90 minus OFD. Why can we say this? This is because the angle at center is equals to 2 times angle at circumference. So here you can see clearly that we've expressed DEF, which is basically E, if you want to think of it that way. In that notation, this is just E is equals to 90 minus OFD, and we already have DFK as equals to 90 minus OFD. Now we have E is equals to 90 minus OFD. Then this means that DFK is equal to E, and that is then proved. And those are the two ways in which you can prove this theorem.